Okay, let's do a quick run through of the homework problems from chapter 6 in the text. So the first problem, there's not a lot of calculation to do. The first problem says a psychology class consists of 32 freshmen. I'll write down that, 32 freshmen and 48 sophomores. I think I spelled that wrong. If the professor selects names from the class list using random sampling, what's the probability that the first student selected will be a freshman? So to figure that out, we need to take the number of freshmen in the numerator and divide by the total number of students. So the total number of students is 80 students. So 32 over 80 equals 0.4. So 40% probability or 0.4 probability. Remember, we take the number of possible outcomes and divide by the total number of cases. So 32 divided by 80. Part B of this question is really kind of confusing, I think. And I don't like the way that the book describes it at all. Basically, it says here, if a random sample of n equals 6 students is selected and the first 5 are sophomores, what's the probability that the 6th student will be a freshman? Well, the book assumes that if you write random sampling in the question, that means that you're sampling with replacement. But that's not really clear, and I would argue that's not necessarily the case. The way the book sees the problem is that if you're sampling 5 students or you're sampling 6 students, then each time you take a student out and record that he's a sophomore, you put him back in again. And you do that 5 times. So you're left at the end with the 6th person, the problem really being the same as the first problem. In other words, you're left with still 32 over 80. I don't think that's really a very good way to ask this question. I think you need to. I think the book should have specified sampling with replacement if it was looking for that answer. Assuming that sampling with replacement is not specified, then essentially what you have is you have the same 32 freshmen, but now you have 5 students fewer sophomores, so you do 80 minus 5, and the probability of now selecting a freshman has increased a bit. I'm not going to bother to do that arithmetic. It's going to be some kind of complicated fraction, but if you had a problem with this question, blame it on the book. Let me write out question 17 so we're all looking at the same thing. Okay, so IQ test scores are standardized to produce a normal distribution with a mean of 100 and a standard deviation of 15. Find the proportion of the population in each of the following categories. All right, so if you looked at the answer in the back of the text, it's going to have you go through this process of converting this to z-scores and then look using the z-score table. We don't need to do that, and maybe if anyone was confused about this, it was because they looked at the answer back there. Instead, we're using that probability distribution calculator, so let me switch to that. For the first, let's see, mean of 100, standard deviation of 15. Find the proportion of the population in each of the following. So the proportion is the same as the probability. So the first case, IQ is greater than 140. IQ greater than 140. So we take a look at the calculator here, and we need to make sure our distribution is set to normal, and our mean on the IQ test is 100, and our standard deviation is 15. So we'll check that, and we want greater than 140 or greater, right, the genius level. So we pick the upper tail. And if you drew this out, as I suggested that you do, the graph should look something like this. We need to change this, however, to 140 because we're looking for scores greater than 140. And now I'll check that, and it's going to return this answer over here, 0.0038. So that's really all there is to it. Let's go back and take a look at the next one. I'll just put the answer down over here. It was probability equals, what was it, 0.0038, I think. Okay, let's take a look at the next one. So the next one, we're looking for IQs between 120 and 140. So let me do what I didn't do last time and just kind of draw this out for you. There's our normal distribution, or something like our normal distribution. Our mean of 100 is over here. And we're interested in the values between 120 and 140. So we're interested in the values in here. What percentage under the normal curve is described in this shaded area? So again, we go back to the calculator. And this time we'll keep the same mean and the same standard deviation, but we'll select we will select between the two tails, the middle area, but we're interested in between 130 and 140. Is that what it said? 130 and 140? I think it was. Oops, 120, not 130, 120 and 140. And that probability, that area, and you can see it's shaded, that probability is that proportion is 0.0874, 0.0874. So let's go back to the other. The probability that a value is between 120, in other words, it's greater than 120, but I always do that wrong. Greater than 120, but less than 140. Probability was 0.08, what was it? 0.087, was it? Well, you get the idea. I'm not going to go back to that page. About 0.08 something. Okay, let's take a look at the next one. So this is similar to the previous one. Oh, by the way, I looked in the book. They give a very slightly different answer to this problem, probably a rounding issue. They have 0.0880. This is close enough. This would translate to, well, actually, it's off a bit, but the answer is correct, unless I entered something wrong in the calculator, which I don't think I did. All right, let's take a look at the next one. The problem is the same, well, almost the same. The strategy is the same. So we draw our normal curve. And this time, we are looking for between 90 and let's say 109. I'll put it about there. The idea here is just that you have some kind of a schematic so that you know that you've used the calculator correctly. That's the whole idea with this. It's the only thing we're worried about. So we'll make that 90, we'll make that 109. So we are back to our probability calculator. Our mean and standard deviation are the same, but this time, and we're also looking between two scores, so we'll enter 90, and we'll enter 109 over here, 109, and that looks like it's just a little shy of 50%, 0.4733, 0.4733. So I'll write that down. Probability, what is it, 90? Did I do that right? Yes, I did. And 109 equals 0.4. I keep forgetting what I write down here. 0.4733. 0.4733. 0.4733. I'm curious if the book agrees with that answer. And it does. 0.4743 they have. 0.4743. Okay, so again, slightly off, but not enough to worry about. And the next one, the next two of these, ask a slightly different problem. They're asking for the probability of getting an IQ score equal to 0.05. So what score do you need? What score do you need for the probability of that score to be greater than 0.05? Let's take a look. Well, let me write it down first. Probability that x is that's the score value, that x is greater than, book uses an exclamation point, 0.05. All right, so here we're kind of doing the opposite. We're starting with a probability value. And we need to find out what numerical value is associated with that probability. I think we can manage to show both screens at the same time. I hope this is visible to everyone. So again, I'll draw my little diagram. Oops. I'll draw my diagram. And now we're given a probability value, so we start out by shading an area. I don't know what that area will be, but we start out by shading an area. Just make it over there. Remember, this is a greater than. It's not between, it's greater than. And we want to find out what that point is. So we go back to the calculator over here. Again, we have normal, we have the correct mean value, we have the correct standard deviation. But this time we want to go back to wanting the upper tail, since it's asking greater than. And now what we do is we enter that value of 0.05, press enter, and we get 124. So a score of 124.6728 gives us that area. So question mark, since the score, I'll write score instead. Score at probability that x is greater than I don't know why it is that the book is giving slightly different answers than the ones that I have, but I'm going to trust the calculator, and the answers are very, very close. All right, and then the last one, which would be E, I think, asks you to do the same thing. I'm not going to bother writing out the problem, the graph rather, but we're given a probability that x is, what is it, greater than? Oh no, that's less than this time. Less than, or just write score. I don't like that question mark thing. 0.75. We do the same thing, except of course we have to change this to be the lower tail, because we have this less than sign over here, not the greater than sign like we did before, but the process is pretty much the same. And that probability there, score equals 110.1173. And let's see, what does the book think the answer should be? Yeah, again, we're off a little bit. 110.05 is what the book says, but our calculator gives us this. I would be inclined to use that the calculator is really giving you the correct answer. Why is that? Because the book is relying on a table, and the table doesn't include enough decimal places to really be able to see a more precise answer. So again, it doesn't matter. The idea is that you know what the procedure for doing this is. And since we obviously did not teach, since I didn't go over how to use the table, there's no reason to ever worry about it. Okay, so let's now go on to question 19. Okay, this question is seemingly rather complex, but it's actually not as complex as it seems. I'm not going to reproduce the whole story here. Basically, the idea is that students have a perceived exam score, and what's interesting is the way in which that perceived score differs from the actual score that they achieved on a given exam. So we see that students in the class who submitted an exam, the mean of that exam was 35. The standard deviation on that exam was 6. Okay, so the first part of the question asks you to calculate the interquartile range. So the IQR, the interquartile range, remember I think it's from chapter 4. The IQR equals the score, I'll write it out, the score at the 75th percentile minus the score at the 25th percentile. Okay, so the first thing we need to know then is the score at the 25th and the 75th percentile. So in a way, that's similar to what we were asked to do in question 16D and E. We need to enter a probability value or a proportion and determine what score is associated with that. So again, if we're using the calculator, our lives are much easier. So we start out, as I've done over here on the right-hand side of the screen. I've entered that mean value of 35, the standard deviation of 6, and I'm interested in the value at the 25th percentile. Okay? Not sure why that is reading like that. Oh, because there's just scores. That's why. That's why. All right. So we're going to enter over here the 25th percentile, 0.25, and that score is about 30.95. I think we'll just call that 30 for argument's sake. So the score at the 25th percentile was 30. And now we want the score at the 75th percentile. And we could keep it on lower if we wanted. We could keep it on higher. It doesn't really matter, I don't think, because we're interested in the score value. But we're going to get now a value of 39. We'll just call it 39 as the value of this at the 75th percentile. So we'll do that subtraction. IQR equals 9. And again, I noticed by checking at the back of the book that they come up with a slightly different answer than we did. But again, we will chalk this up to the difference between using the calculator and using the tables as the book has you do. All right, what's the next part of this then? The next part of the problem is rather tedious. It asks you to compute the z-scores for each of the actual exam scores in the data set, and then to compute the percentile rank for those scores. I'm not going to go through all of them, but we'll go through a few of them. actual score, z-value, and the percentile rank. Okay. Remember, the percentile rank is the percentile value of a given score. Okay? So that's what we need to compute, the percentile value, a probability value, a proportion value for that particular score. So let's take the first one. I'll write a couple of these out. 33. We did 30. I reversed those. The first one should be 33. The next one 30. The next one 36. All right, so remember that our z-score is equal to the value minus x bar, the mean. In this case, it's a population mean because he's not sampling, and divided by the standard deviation, sigma. All right, so the first one, we're going to have what? We're going to have 33 minus the mean value was 35, divided by the standard deviation was 6. So that's 2 over 6, or negative 2 over 6, and that's negative 1/3, or negative 0.33. And the next one, 30 minus 35 divided by 6. So that will be 30 minus 35 is negative 5 divided by 6. And that is equal to negative 0.83. Let me check that. Okay, that checks out. And the next one, we have 36 minus 35, and that will give us positive 1 over 6 and a value of 0.17. All right. So, we could keep going for all 15, which we'll have to do actually to get to part C, but I'm going to cheat a bit on that. But let's show you how you figure out the percentile rank. So in this case, again, what we're doing is we're entering. Okay, so to figure out the percentile rank of a score, what we're going to do is we are going to still use our calculator. And this time, since you bothered to create all of those z-scores, we may as well use those. So in that case, we need to change our value for mu, the mean, and our value for the standard deviation to use what we expect with a z distribution. Remember, we're no longer using the actual mean and actual standard deviation. Because we took the time to create those z-scores, we're going to use them to compute our percentile rank. Now, remember first of all that a percentile value is the score. A percentile value is the score such that a given percent of all of the scores are less than that score. Okay? So to get a percentile value, we're interested in that shaded area. Or it might be that we're interested in, we start with this value and our percentile score is the actual score. In this case, however, we're not looking for a percentile value. We're not looking for a score. We're looking for a percentile rank, which is a probability value. So what we need to do then is we need to make sure that we are entering our score. In this case, it will be the z-score, and we're going to get our probability value over here, our percentile rank value over here at to the right of the equal sign. So for the first one, I'll type in negative, what did I type in? Type in negative 0.33, and gives us a percentile rank of 0.37, or your book prefers to put this in percentage terms. So, okay, that would be the answer there. And we'll do the same thing for the next one. we had a z-value of negative 0.83. Okay, so that will be 0.20 or 20%, the percentile rank. And the last one that I did, you'll be doing all 15, that was 0.17, 0.17, and again, that would be, we'll call it 0.57. We'll round that, and that gives us about 57%. So what is this really telling us? Well, it's telling us that 50%, 57%, this 57% of our students scored 36 or less on the exam. That shows us over here that about 20% of our students scored a 30 or less on the exam. And finally, this one over here, 37% of our students scored a 33 or less on the exam. Okay? So that's what's going on. What you need to remember to do is to make sure that you're looking at the lower tail over here. You're looking at the lower tail to get the correct percentile rank value, the correct percentile rank value. All right, I'm not going to go on to part C because that would mean I'd have to compute all of these scores. But what's interesting here is that it turns out that the students who actually did not that well, the students who were in the bottom 25%, actually had a higher perceived, or I should say, that that their perceived exam score was higher than their actual exam score, whereas the students who scored well in the top 25% believed that they had scored lower. You may be familiar with something called the Dunning-Kruger effect. And the Dunning-Kruger effect basically says that people who don't know a lot about something think that they know more about that thing than people who actually know more about that thing. If I know a lot about something, I'm likely to underestimate the amount that I know. And if I don't know much about something, then I'm likely to overestimate what I know. So it's kind of an interesting phenomenon. You'll see it all over the place. It's called the Dunning-Kruger effect. All right, let's go on now to question 21. So this one is not that different than some of the others that we've looked at. So we've seen a number of problems like this one. A report in 2016 indicates that Americans spend between the ages of 8 and 18 spend an average of 10 hours, on some kind of electronic device, with a standard deviation of 2.5, and then it asks us to figure out a bunch of different things. So the first one is, what's the probability of selecting an individual who uses an electronic device for more than 9 hours a day? So, as usual, we will draw our little diagram to make sure that we're on the right page. And again, your book will have you convert these to z-scores, but we don't bother with that. So we want to know more than 9 hours a day. So I'll put in, the mean is 10 hours a day. So we are interested in this area over here. Oops. We are interested in this area over here. So to do that, we'll go back to our calculator and I will enter that 10 hours a day. And I will enter that standard deviation of 2.5. And I will make sure that I'm looking at the upper tail because we want it to resemble this here. And we'll change this to a 9. and our probability is about 0.6554. Okay, about 0.5654 that I have selected of selecting someone who watches TV for more than 9 hours a day. So the probability of selecting anybody who watches more than, it should be the other way around, more than, 9 hours, equals 0.65. Okay? That's part A. Part B asks us the proportion that spend between 8 and 12 hours a day. So that's the probability that X is greater than 8 but less than 12. So we need to change this to the middle of the distribution, and we need to change these values. That one is going to be 8, and this one is going to be, 12? So that probability is in the middle and about 0.57, or it's about a 57% chance of selecting someone who watches between 8 and 12, or the proportion that watch between 8 and 12. And by the way, just to be clear, that this graph is for this one, and let me just quickly draw a graph for the other one. That's going to be between 8 and 12, so we are in the middle area over here. And again, you'll see that my graph that I've drawn matches the graph in the distribution calculator. And I have a feeling, I haven't looked at it yet, but I have a feeling that the next one is going to ask us, it's going to ask us what the interquartile range is for time spent using electronic devices. So to figure that out, we need to enter instead probability value over here. Oops. So again, to calculate that interquartile range, IQR equals the score. In this case, it is the number of hours, the score at the 75th percentile, minus the score, the number of hours, in this case, again, at the 25th percentile. And we need to figure out then that 75th and that 25th percentile. So 75th percentile is going to equal, what do I have here? I have 10 and 2.5. 10 for our mean, 2.5 for our standard deviation. And I need the score at the 75th percentile. So I'm going to work with the lower tail. And that score is going to be 11. What is it, 11.68? And the score at the 25th percentile so we'll change this to 25. Keep everything else the same. So 0.25. That gives us a score of 8.31. So the IQR is equal to the 25th subtracted from the 75th, and that will give us a score of 3.37. So the IQR is 3.37. And I think that, that's the last one for 21, and there's one more to do, and that's question 23. And for question 23, they are trying to get you to start thinking about inferential statistics. They're trying to start to get you thinking about inferential statistics. We have a smart drug, and we're giving the smart drug to people, and we want to see whether or not their IQ is different from the or what the probability of getting that IQ would be, of the individual having that IQ score if he's taken the smart drug. So we start out with the IQ average of 100, and again we know that these are normed to 115, 100 for the mean, and 15 for the standard deviation. So what's the probability of getting a score greater than 145? So the probability of getting that a score is greater than 145, and that's real simple to do. We're looking at the upper tail because greater than, and we'll have to make sure we enter the correct mean of 100 and the correct standard deviation for the IQ test of 15. And we want the probability of a score greater than 145. It's going to be quite low, I think. Yes, it is, 0.0013. So if you were given this smart drug and your score was 145, there was a very small chance that was due strictly to chance. Very small probability that was due to chance. What if your score only went up to 110, though? And again, this is because we're in chapter 6. We will learn, or maybe we already have learned, that there might be other ways to do this study. We might compare your score before and your score after taking the drug. That might be a better way to do that, but in chapter 6 we haven't gotten to that yet, so we won't worry about that. So that is a fairly high probability that we could have gotten that score strictly by chance. Okay, and that's a wrap on these questions. I'm sorry that question 22 really took a lot of time to calculate. You need to calculate all those z-scores and then plug all those z-scores into our probability calculator. But hopefully you're up to speed with the procedure now. All right.